Well, thanks, Joseph. We are continuing our discussion about FeenoX, which is a cloud-first, free and open source finite-element tool. Last week, we went directly to the practical aspects. We went through a couple of tutorials, hands-on tutorials, and I had explained that time that whenever I give talks and I start with theory and then practice, by the time that I get to the practice, people are bored or they even left. So this time I try to do it the other way. So this will be like the theoretical or the explanation of the rationale behind what we had done last week. One comment here is that this presentation is hosted on GitHub. So if you go to this link here, you will be able to see the sources in Markdown now. So any link that I will post here, you can find in this public repository. So let's start with breaking up these words that I said. If you recall, last week we executed FeenoX, and it will tell you what it is. So it's a cloud-first, free, no fee, no X, Unix-like finite-element-ish computational engineering tool. So let us break that up. Well, these are an explanation of that the last X makes it prime with Unix and Linux. This will be important later. No X means that there's no graphical interface because it's cloud first. We already talked about this last week. Fee, no, in this case means that there are no fees involved, at least for running or downloading or compiling the solver. It's free, as in free beer in this case. Well, some other examples here. But let's break up the cloud first, which is not the same as cloud friendly. FeenoX is cloud first. And here we say that cloud, of course, it's somebody else's computer, but in this case, it's somebody else's computers. So the key here is that you can use other people's computers, meaning that you can scale up and you can solve problems that you for sure might not be able to solve in your own computer. So it's somebody else's computers, not just one computer. It's free and open source, which doesn't mean gratis in the sense that about price. So free and open source, they are slightly similar. It's not about price. It's free as in freedom. It's about having freedom. We will explain it later. And the open source part is about transparency. In this case, FeenoX is both free and open source and gratis in this case, but it might not necessarily be. Finite-element-ish, the main application of FeenoX will be to solve finite element problems. I mean, problems formulated using a finite element formulation, but in principle, you can use it to solve finite volumes problems. We are going to show how to solve ODEs, which are not partial differential equations, and no finite element formulation is involved, and even generic math problems that we're going to solve Fibonacci sequences that don't even have differential equations in them. And well, it ends up with computational engineering tool. We as engineers know that the right tool for the right problem, right? It's a word game. Let's first take a minute. How do we write papers or reports or documents? So first approach would be to use Microsoft Word. We know the aesthetics of words, they are not good. You can convert it to other formats, but not so much. It's the traceability of the source is like way worse than any other approach. We end up with naming files, final, final2, final. Yeah, we have been through that. It's not mobile friendly, it's not collaborative, it's not open, of course. The only pro is that it's friendly. On the other side of the spectrum, we have text or LaTeX. It has way better aesthetics. It can be converted into some other formats as well. If we use Git, we can trace it. It's not that mobile friendly. Collaborative, well, if we use GitHub or something like that, you can do some collaboration. It's open for sure. It's free source. It's not that friendly. Now, what do we have in the middle? Well, Google Docs. So it's like Word, but in the cloud or in the web-based environment. So the statics is pretty much the same. Compatibility is the same. It improves a little bit the traceability. It is mobile friendly, less collaborative. It's not open. It's running on the cloud, and it's friendly. And in here we have Markdown. So for statics, if you convert to text, you have the same statics as text. You can convert to HTML and EPUB and a wide variety of formats. You can trace it very much like with text using Git. You can do it mobile friendly. It's easier than text. You can do it collaboratively. Again, if you use GitHub or something like that, it's open and it's not as friendly as Word, but it's not definitely as worse as text directly. That's how we write documentation, technical papers involving math and that kind of stuff that we engineers do. Now, how would they perform engineering computations? On the left side of the spectrum, we have desktop programs with GUIs, very much like Microsoft Word. They are friendly, but they lack a lot of the good stuff that we engineers like. On the right hand of the spectrum, we have these advanced libraries that you have to compile, you have to tweak, you have to know how to use. They're very flexible, powerful, scalable, and a lot of the good stuff, but they are definitely not friendly. Well, we have now been seeing a lot of web front ends for finite-element software. I can mention CAPlex, which is the one that I wrote, but there are some others. They work very much like Google Docs. So they are similar to desktop GUIs with the mobile friendly and collaboration tools. And here's what we are going to talk about. So FeenoX here is like, FeenoX to traditional software is like Markdown to traditional way of doing stuff. So it sits in the middle. It provides a lot of the good stuff, and it's more or less friendly. It's not as friendly as a point-and-click software, but it's not a library that you have to compile or even write the integrand of the weak formulation you're wanting to solve. We saw that last week, and we're going to dig into a few other examples. So this is the way that I personally like to see FeenoX. It's in the middle of the left and the right side of this spectrum. Now, some other clarifications about free and open source software. They are more or less the same if you go through the definition, mostly because the definition from the open source initiative is taken from the Debian free software guidelines. So the key word here is freedom. You're free to modify the code. You're free. If you don't know how to modify, you're free to hire somebody to modify it for you. If you never had access to the source code, you would never be able to modify it, and you would never be able to hire somebody to modify it for you. Same thing for open source. So you can see what's going on. You can hire somebody to see what's going on inside the code if you don't know how to code or you don't understand code. So if you have free and open source thing, you have freedom and you can do stuff. But this doesn't mean that when a code has a source available, it's automatically free software. For instance, there's a case, this is Serpent, is a code for calculation, for doing Monte Carlo calculations of neutron transport, like very much for nuclear reactors. The source is available, but they will give you the source only after signing a non-disclosure agreement. So that doesn't classify as open source or free software. And my other example is that Calculix, you can go and download the source code, but it's written a mixture of Fortran 77 and C, and it's very hard to follow. It's like, I think that only the original autocad can read it and modify it. So to me, it doesn't also classify as free software because I don't have the freedom to modify it, and I don't have the freedom to hire somebody to modify it because it's very hard to understand. So again, it's not about money, it's not about licenses, because free and open source software do have licenses that you have to comply. But again, it's not about money. The importance is that you can see what's going on. You can hire somebody to tell you what's going on. You can modify it, or you can hire somebody to modify it for you. So at the end of the day, it might be more expensive than the counterpart, which is called private software. It's not commercial software. So the opposite of free and open source code, it's not commercial code like the talk that we saw earlier this week or last week, I don't recall. It's not commercial code. It's private because they private you from the freedom that you might have if you used free software. So at the end of the day, you might need to invest more time, more people, more money to make it work, but it's worth it in terms of accuracy and flexibility. And remember that at the end of the day, it is your signature that will appear in the engineering reports that you're going to create. So it's up to you if you want to believe the manual of a software that doesn't come with the source code, or you are going to trust that the solver will be solving the right equations the right way, because you can trust that somebody is going to check on it, on the source code, actually, not just on the documentation. Now, let's play a little game with FeenoX. So what I like to do is I wrote a fictitious software design specification that will act as a fictitious and imaginary request for quotation, like assuming, I don't know, a company or a national lab or some institution is going to go into an international tender, and they will list the requirements, and then they will choose a computational software that better fits that requirement. So there are 4 sections in this fictitious tender, which you can find here if you go to simplex.com/FeenoX/doc and see and look for SRS, the software design, software requirement specifications. It has these 4 sections that we will go through. And in the green part, it will be like the software design specification. That will be like the quotation and what, in this case, FeenoX, not what, but how is FeenoX going to fulfill all these requirements. So in the next slides, on the left, we will have the requirements, and on the right, the proposal that FeenoX is proposing. So the introduction, the requirements are the tool should be applicable to industrial problems, and it has to be open source to allow third-party validation and verification. That's a requirement. It has to be open source. The first version should handle some problems, but it should be extensible to other problems of formulation. So it has to be free, so people can be hired to code extensions to other problems. For instance, in the first case, we are going to solve linear elastics, heat conduction, modal problems, but we are not solving electromagnetism. But then, since the code is free, what FeenoX offers, it's GPL-v3+, and it depends only on free and open source dependencies. You can compile it by just download it, whatever other libraries that you need from the internet, freely. So since it's free, somebody can be hired to add electromagnetism or CFD. Yeah, and it should be state-of-the-art cloud first. This is our requirement. So FeenoX provides this. Scope, the requirement is that the problem should be defined programmatically. The problem to be solved has to be defined into one or more input files. We can have these formats, or an API for a high-level language like Python and Julia. These are the requirements. There is no need to include a GUI, but the tool should allow a GUI to be used. So the mesh can be an input. It has to include documentation. Now, if you recall last week, there is no GUI in FeenoX. It's a binary executable. It works like a transfer function. There is a set of input files and a set of output files. So the input files are fed into the binary and the output files are written into whatever support you need. But there's no need to recompile the binary. Once you compile the binary, that very binary will read all a wide variety of input files. It's not like a library where you have to recompile to solve a particular problem. We already went through this. So in FeenoX, the input file is an English-like text file with syntactic sugar, where nouns are definitions and verbs are instruction. We currently don't have a Python or Julia API, but we already took that into the design, and eventually we can implement one. So the meshes is separate. It can use Gmesh or anything that write mesh. And there's the possibility to use the GUI. If you go to cplex.com, you will see that this is a web-based GUI. It's not actually for FeenoX, but for the previous version, but it works the same. So let us illustrate the transfer function and the English-like input. Say we want to solve the Lorentz system. This is not even a PDE, it's an ODE. So we have to solve this set of differential equations for this time range with these initial conditions and this set of parameters. Now we have an input file. We define a phase space, X, Y, and Z. We define the end time here. We define the set of parameters here. We define the initial conditions here. We define the equations to be solved. And then we ask FeenoX to print time, X, Y, and Z. So there's a one-to-one correspondence. The equations are here. The time is here. The initial conditions are here. The parameters are here. So if we run FeenoX with this input file, we get 4 columns, T, X, Y, Z. And then we can plot this and we get the output of Lorentz system. So that means working as a transfer function. Reads input, writes output. Now, there's some philosophy behind it. It's the Unix in particular, we didn't mention too much last week. So the idea is that 2 points, make one program to do one thing well. And if you will need to do some stuff that it's complex, start from scratch instead of adding features to all programs. So expect the output of every program to become the input to another. And don't clutter the output with extraneous information. This is the idea of a filter. It's like transfer function. It will be like a Unix filter. So write programs that do one thing well and do it well. So we're going only to solve equations. We're not going to mesh. We are not going to a user interface. We're not going to pre-process. We are not going to post-process. We're going to read an input, solve a problem, and write the output. So write programs to work together. In the previous case, what we see Lorentz, this is plotted with gnplot. We can use matplot, we can use whatever. So the output is ASCII, and the output of this execution can be post-processed with other tools. So write programs to handle text string, because that is an universal interface. This is text, and almost any plotter can understand text. So about CAE, if you recall, even though many mainstream programs they were designed in the 70s, so 50 years later they still do not make just only one thing well. They have GUIs, they have preprocessor, they have a lot of complications. They add features into a single problem. They don't expect to play well with other programs. They do cluttered output with information like ASCII art or page separators or banners. You can see that if you know what I'm talking about, if you came with some output of these programs. They usually don't like columnar and they use binary output, input and output formats, and they insist on interactive output. In this case, we're going to focus on the rule of silence and rule of economy. If the user doesn't want to have any output, he or she won't have any output. It's far cheaper to rerun a course problem and just get the answer that you're looking for than to have to browse through thousands of lines, because usually back in the 70s it was far more expensive to run codes and CPU usage. So anything that a code would calculate, it would be printed into the output. So at the end of the day, the engineer will have to browse through thousands of lines. So that doesn't make sense. Today, you just rerun and you just get the output that you want. So this is an example. So here's this cplex.com web interface runs into an iPad. So FeenoX can use a GUI. Another section will be the architecture. The requirements are that this should run on mainstream cloud service. That means GNU Linux. It should run in multi-core CPUs with a few gigabytes of RAM. So the code should be compiled with the standard compilers, libraries, and dependencies. So anything that you might need to install should be like in apt-get or RPM, whatever common Linux repositories. This is what we propose. So FeenoX is actually a third system fact. Like I started this more than 10 years ago. Then I was version 1. Then I wanted to add more features, and then I rewrote it from scratch, like in version 3. We've been through this. So any third-party math libraries like GNU GSL for this means that GNU Scientific Library, PET-C, SLAB-C, and Sundials to solve problems. They are available. You can do apt-get and install the compilers, all the dependencies, and then you will be ready to compile. You can clone the sources directly from GitHub, and then it uses auto tools and automake. So configure make, that's standard Unix, and you should be able to get FeenoX compiled from source. The idea here is that a small problem should be run in single host to check input, but large problems should be split into several hosts, like in parallel. Well, we tested this. We even ran FeenoX on Raspberries and some other architectures as well. Parallelization, we're working on it, but it's everything baked into the decision. Into any design decisions, parallelization is in there. We've been through this just to complete. We can solve a maze. How? Let's say we do know the start and the end, like solving a maze on a placemat. We create the maze, then we do some steps to get a mesh out of it. Then we solve the Laplace equation with these boundary conditions. If you recall, this was the input file that we used solving Laplace with these boundary conditions. We solve the problem, and we start at the inlet and follow the gradient to follow our way out of the maze. This works pretty well with mazes that are not just rectangular, but have other shapes as well. That's an example of flexibility. Another requirement is that it has to be automatically, you can automatically compile the tool from source, like running into scripts. There should be preferably pre-compiled binaries. They have to be available online, and the execution should allow, of course, remote execution. And you can have scripted or parametrics or optimization loops. There should be ways to read the data from this parametric loop and write the results back. We will go through that. So it's very easy. This should be, if you never compiled something from source, this will be like Chinese for you. But if you did, these are like pretty much common commands to compile stuff. And if you don't like to compile stuff, then you can just download the binaries and run them directly. Everything is Docker friendly, it's execution friendly, it's remote execution friendly. And let us see some example of execution. So direct execution here, for instance, 3 ways of getting the first 20 numbers of the Fibonacci sequence. Way number 1, a function with analytical solution. If you recall, this function of n, that it's equal to this golden ratio to the nth power minus this, divided the square root of 5th. If an integer comes here, then the evaluation of these functions is the nth Fibonacci number. So we are going to print this function from 1 to 20 into steps of 1 for the argument. This should print the first 20 Fibonacci numbers. Another way, Well, we define a vector of size 20, and we say that that vector for I equal to 1 or 2 will be equal to 1, and from 3 onward, it will be the sum of I minus 2, I minus y, and then we print the vector. And as an iterative problem, in this case, we ask FeenoX, okay, we're going to do some static steps, so 20 steps. And then if the step is equal to 1 or 2, we initialize these 3 scalars variables to 1, and for the rest of the steps, we're going to update this fn to the sum of these two, and then we do like a ladder, and then we print this step and fn. So we execute this FeenoX with this input file, and we just see the output. We write a file named 1, but also we see the output in the terminal. So 1 to 20 and the 20 evaluations of fn. Then we call Fibo vector, which is this input file, and then we redirect the output to 2. Do the same with iterative. We redirect the output to 3. Then we take the diff between 1 and 2 is null. The difference between 2 and 3 is null. So these 3 files, the output of these 3 input is exactly the same. So this is like the rule of you can do stuff in different ways. Instead of just direct execution, in this case, we have a bash file. We are going to do some force. The important thing here is that when we call FeenoX with this cantilever.phi, which is this input, we pass 2 extra arguments, which in this case, element would be T4, T10, X8, X20, whatever, and C is going to be a number between 1 and 10. So this will be expanded as $1 and $2. So $1 will be T4, T10, whatever, and $2 will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is a very simple problem. So when we run this script, we're going to call FeenoX several times for each combination. And then in this case, we plot the number of nodes, the vertical displacement at the tip of the cantilever. So we are solving a cantilever with a boundary fixed and a traction on the other side. And then we can plot. So we have the numbers of nodes here, we have the displacement, so we see what we already know, that first order elements are far stiffer than second order elements. And if you want to have like a real representation of your bending case with first order elements, you need to go way a lot high in the number of nodes. While if you use directly second order elements, you will have a reasonable result with a bunch of nodes. Now that was a parametric run where we knew that we wanted to go first to T10, then to T4, whatever. In this case, let's say we're going to solve an optimization loop. We have this geometry, this is a tuning fork, and we want to know which length should we manufacture the fork in order to have a zero mode resonance frequency equal to 440 Hertz. So in this case, we can do some Python. I'm not going to go into the details, but the input file is really simple. So in this case, it's like it's looping and creating a new mesh for different lengths of L1. And then when you plot it, as you iterate, then you converge to a length that will give you the 440 Hertz. So that finishes the part about how to invoke it and that the tool should allow parametric and optimization runs. About efficiency, scalability, and flexibility, well, still it's under development, so we're not paying too much attention to rule of optimization, but there are a couple of benchmarks where we see that FeenoX is as fast or even faster than other tools. It's written in C, not in C++, not in Fortran. And there are reasons for this. They are discussed in the documentation. And some examples about flexibility. So, for instance, let's say we want to solve a one-dimensional thermal slab. So temperature at the left will be 0, temperature at the right will be 1, uniform conductivity, and we want to know the temperature at half. This should be 0.5, by half, 1/2 the temperature at that point. Well, this is the mesh. This is the input file, We run Gmesh to get the mesh, we run FeenoX, and we have the answer. So how does this work? Here we ask for a thermal problem in 1 dimension. We read the mesh, which is created with this geo file. We set a uniform conductivity. We said that the boundary condition at the left is t equal to 0. The key here is that this left is this left, this right is this right. We solve a problem and then we print t at 1/2. The key here is that the mesh file defines that the characteristic length is 1/3. So we have a node at t equals 0, a node at 1/3, a node at 2/3, and a node at t equals 1. We don't have a node at t 1/2. But nevertheless, we can ask the temperature at any arbitrary point, and FeenoX will interpolate it for us, and will give you the right answer here. What if now we wanted to test, okay, this will be like the uniform conductivity. What if conductivity is not uniform anymore? Now let's have this problem. The boundary conditions are the same, the node is the same. Now we include what? Something that is called $1, which comes from the command line. So if $1 is uniform, we include these lines. If it's space, we include this. And if it's temperature, we include this. In this is the case that we already saw. So in this case, conductivity can be a function of space, 1 plus x, and the solution will be this one, the analytical solution, I mean. And if it depended on temperature, like 1 plus a constant time the temperature, the analytical solution is this. So everything is an expression. If you remember, last week we said that everything is an expression and similar problems need similar input. So these are similar problems, they have similar input. If we now run FeenoX with this input file and then we pass uniform space and temperature, like 3 runs, then we can see the blue curve is the case for conductivity equal to 1. In this case, exactly the nodal values, the analytical solution coincides with the finite-element solution. The green one is for space dependent, and we can see here that we have linear interpolation between the nodes. Recall we have 4 nodes, one here, one at 1/3, the other one at 2/3, the other one at 1. So these are the combinations. At the locations of the nodes, the solutions match. But the interpolation, well, since we are using first order elements, the interpolation is linear here, while the analytical solution is not linear. But this is another example. Finally, more flexibility. We are going to solve a 2-dimensional problem where we have this mesh of 2 squares which are in contact. We're going to solve a thermal problem. Here, you can see here that this square has triangles, this square has quadrangles. The material named yellow will have a conductivity that depends on temperature. The other material, we have a conductivity that depends on space according to this function. And this function is given like x, y, and conductivity without any topology there. So scattered data that will be interpolated at the locations where we need the conductivity. Yeah, the yellow material will not show any power. The other one will dissipate some power in the bulk, like 1 minus something that depends on temperature. So this problem is nonlinear. In this case, these 2 problems were linear. This problem is not linear because the conductivity depended on the temperature itself. And FeenoX can tell that in this case, conductivity depends on temperature. So it switches automatically from the linear solver to the nonlinear solver. In this case, it will also be smart enough. We have some boundary conditions given by expressions at left, bottom, right, and top. So these 2 are Dirichlet conditions, these 2 are Neumann conditions. And well, this is like the temperature distribution, and this is how the conductivity looks like, because if you recall, the conductivity depended on the space and on temperature here. This is the distribution of temperatures. So here we can show that we have multi-materials and properties depend on the space or even on the unknown itself. Transit problems, this is an Eiffen test. The key here is that this is a 1-dimensional case. Temperature is kept at equal at 0 here, and it should follow a sine of pi time divided by 40. Again, the initial condition is here, it's 0. Boundary conditions t equals 0 at left. This expression at right, the conductivities and the material properties are here. The end time is equal to 32 because the output is the temperature at point C, which is located here at 0.08 meters at 32 seconds. So we asked to solve the problem. While we are solving the problem, we print T, the time increment, because it's adaptive, the temperature at 0.1, and this, which should be equal to this sign, and the temperature at the point C. When we're done, we just print again the temperature at point C. We run this, and we get that the result is equal to 36 point something, which is nearly what the target of the problem is. Again, illustration of flexibility. Extensibility, this is something that the tender asks for. Well, in principle, there's a template, and each formulation, each problem, Laplace, heat transfer, linear elasticity model, even neutronics has its own directory. You can copy a directory and use it as a template for a new formulation. You can remove a directory and recompile, and magically FeenoX will not be able to support that problem anymore. There are some things that we want to do for the future. Some other example about how well FeenoX plays with other software. In this case, we're going to solve the Laplace equation over a square, but the point here is that we're going to write the very same result as a .mesh file and as a .btk. So the very same problem, the very same answer, you can post-process it with Gmesh or with ParaView, whatever you like more. Another example of that, how FeenoX works well with other programs. Interfaces about input. Well, we've been through this. This is a self-evident ASCII input. We've been here, expansion of command line arguments to give more flexibility. This is a one-to-one correspondence between the formulation, like written in a sheet of paper. This is a Nathan test case from 1990. It says, solve a linear elastic solid. Yeah, we're going to solve a mechanical problem. This is the mesh that you have to use. Okay, read the mesh from this mesh file. The loading is uniform normal pressure of 1 megapascal on the upper surface of the plate. Okay, VC upper V equal 1. Boundary condition form restrictions. Okay, this faces a zero displacement in this degrees of freedom, whatever. You can have one-to-one between these 4 lines and these 4 lines. Material properties are uniform, isotropic, so E equals something, nu equals something. Solve the problem, and then what the output is. Okay, direct stress sigma yy at point D. So sigma y at point D is sigma y evaluated at the coordinates of point D. Then you run this input file, and then you just get the result that you asked for, nothing else. Everything is an expression. This is another case. In this case, there's a temperature distribution given by an algebraic expression of x, y, and z. Well, in this case, this says that the temperature distribution is equal to the square root of that plus c. So the square root of plus c, and that's it. You don't need some u temp or something else. You have a temperature, then you have a thermal expansion coefficient here. You solve the problem, you get the result. So in this case, the target problem will be stress at some point equal to minus 105. You run it, and you have that sigma, it's equal to minus 100. The output, clean output expected. Do not clutter the output with ASCII. These are the requirements of this fictitious standard, and the output should be interpreted by both a human or a computer. Well, we've been through this. We can play well with nuplot. We can play well with matplot. We can play well with Gmesh, with ParaView, whatever. Another example. So since we have these print instructions, you can print a combination of verbatim strings and numerical data. We can, for instance, in a model analysis, write something that matches the markdown specification of a table. So if you run this case, this is a snippet of a larger example that you can find on the FeenoX webpage, then you can just render a markdown table directly. You just copy the output of FeenoX, paste it into markdown, and then you have a real table. If you don't like Markdown, then you can do something else and write LaTeX. This is an example of a report from a multi-billion agency in the US. And you can say this is either Excel or Word. The same thing that I did a couple of years ago through LaTeX, coming from the output of FeenoX. It's far more aesthetically pleasant to go through LaTeX, and you can do it directly from the output of FeenoX. Well, and then just to finish, the requirements about quality assurance and reproducibility and traceability. Well, we have everything tracked by Git. It's hosted on GitHub. When you run the binary, it will tell you which hash or which version you're using. So you can then go and find the actual source tree that gave rise to that binary by using this hash. You can see, you can ask FeenoX to report its own version. There are requirements about testing. Yeah, well, we have tests. We do some validation runs, not important right here. Verification and validation, this should be very important, but I will go through it. So verification, it's a word game, checks that this code solves the right equations, and validations that it solves the right equations. Well, we can do a lot of things, but since everything is an expression that gives rise to the direct application of the method of manufacture solutions, where you propose what the solution of your problem is, and then you go backward, which is you take a couple of partial derivatives, and then you see what for instance, the source stem should be in order for your problem to have that solution. So then you have the actual solution, and then you can verify the numerical solution with the analytical solution up to the precision that you want to refine, and then you can compute the slope of the convergence. And if that matches the theoretical convergence, you're solving your equations right. We can do that because everything is an expression. So we can come up with a load that depends on space, on time, whatever you want it to depend. Documentation, well, yeah, we have a lot of things. We went to the tutorials, we've shown the manual and some other examples if you go to the web page. And to finish, so nowadays, cloud first approach. It's not just cloud friendly that you can run on the cloud. There are a lot of things that you have to take into the design to make it cloud first. Scalability, parallelization, a lot of things. Well, now that we've gone through a lot of examples, maybe I can make clearer my point that FeenoX is to finite-element analysis, what Markdown is to documentation. So far, it's the only tool that fulfills all the requirements of these fictitious requirements, which are, I know, very reasonable requirements. But the first requirement is that it has to be free and open source, cloud first, and it has to provide all the things that it's required. I don't know any other tool that complies with that, about extensibility, flexibility, and that stuff. And well, again, Unity's philosophy, do one thing, but do it well. In this case, what we want to do well is read a mesh, solve a problem by the outcome. And if you guys are interested, please help us build a community. Go into this GitHub page, go to the discussion, post questions, try stuff, compile things, see if they are broken, and ask for help. So yes, what are clouds made of? Linux servers mostly. And to finish, I would like to share a video, 30-second video, which I don't know where it is. Should be here. Now, these are the equations that we have taught about pendulums in college. But now my experience is that real-life pendulums are like this. And there's a hint. The period dots depend on the mass of the ball. And well, thank you very much for your time. That's the end of my presentation.
Thanks, Jeremy. Great talk. Really insightful. Any questions from the audience? In any other case, Jeremy, thank you so much for the 2 talks. Really much loved the first one, and I also love the second one. And I hope to see you in the future in another cohort. And as
thank you for your time. Thank you for your time, for your invitation, and thank you for featuring FeenoX as the tool of the week in your last newsletter. I enjoyed it very much.
Absolutely. Thank you so much. I wish you an awesome rest of the day, and I hope to see you in a second call in the future, Jeremy.
Sure. Looking forward to it. Bye-bye.
Take care. Bye-bye.